Very often, the questions that are going to be of interest to us in whatever field we happen to be thinking about are going to be questions that compare multiple different populations. So if we think through the parametric framework, we might use a two-sample t-test to compare the means of two independent populations. We're going to ask ourselves, is the population mean from our first population equal to the mean of the second population? Or are they perhaps related in some other way? Because of the utility of these types of questions, of comparing one population to another, it's quite helpful for us to be able to run these types of tests in the non-parametric context as well. So the two-sample independent t-test is a parametric technique that's going to compare two different distributions' locations. Now, the Mann-Whitney U-test is going to provide a non-parametric counterpart. It'll be subtly different, but it's going to allow us to answer similar questions as those that we can answer using the two-sample independent t-test. So when we're thinking about these tests, what we're really thinking about is the comparison of distributions. So in parametric hypothesis tests, we can compare the means of two different distributions. For instance, with the t-test, we might run the test of the null hypothesis that mu x is equal to mu of y, right? If it is assumed that the two distributions are otherwise equivalent, then if we check if their means are equivalent, that's also going to be checking for the equivalence of the distributions. So if we make the assumption, for instance, that both populations are normally distributed and that they have the same variance, then testing are their means the same is the same thing as saying, are their distributions the same? Because if they're both normally distributed and they have the same mean and they have the same variance, they have exactly the same distribution. We could directly consider the distribution of x as being the same as y. We could think about this as being the question that we're actually answering here, right? With a t-test, if we are assuming this normality, if we're assuming that the distributions are otherwise the same, we can think about the t-test as asking, are the distributions of x and y actually the same? The Mann-Whitney test is going to provide a non-parametric test to address this specific question. It's not going to require us the assumption of normality or the assumption of equal variances. Instead, we're simply going to look at two different samples from two different populations, and we're going to say, is the distribution of the first sample the same as the distribution that produced the second sample? So specifically, we might consider testing the null hypothesis that their CDFs, fx and fy, are going to be the same versus the alternative that they're actually different from one another. So what does the Mann-Whitney U-test actually look like? To set up, we'll suppose that we have x1 through xn that are drawn from some unknown distribution, but we'll denote its cumulative distribution function as fx. And we'll also suppose that we have a sample from y, this time with a sample size of m, that's drawn from a distribution with a CDF of fy. With our Mann-Whitney U-test, we are going to be testing the null hypothesis that these two CDFs are the same. Now, the Mann-Whitney U-test is also known as the U-test simply, or also as the rank sum test. So all of these refer to exactly the same test procedure, and they're all going to be testing this null hypothesis that the distributions are actually the same. The alternative is going to be given by the distributions being different, but we have this sort of added requirement here. And so what is this added requirement? Well, we need to require, in order for the Mann-Whitney test to hold, we need to require that under the alternative hypothesis, the probability that x is greater than y is not equal to the probability that y is greater than x. So this is something of a technical requirement in order for us to run this hypothesis test. But the basic idea here is that we can't have two different distributions that are symmetric and centered on the same point, right? One of them should be more likely to be bigger than the other if their distributions are actually different, okay? And so when we're asking, are the distributions the same versus are they different, what we're really thinking about is, are they the same or are they different in such a way that they're not actually symmetric in terms of this probability statement here? Okay, so it's a subtly different test, but it's typically sufficient to just think about testing, are the distributions equal or are they not? This test is not going to be able to tell apart two different symmetric distributions that are centered on the same value and then reject the null in that sense, right? So in that case, we're going to expect that it will return that we cannot reject the null. Now, there are also times where this test can be used to test for equality of location. So testing the null hypothesis, mu x is equal to mu y. This is going to map a little bit more directly onto the two-sample t-test, and so it's interesting to consider what is actually required here. In order for us to make the Mann-Whitney test this hypothesis, we have to be willing to assume that the CDF of x is going to be given to us by the same CDF as what we have for y. So f of x is going to equal fy, except instead of being at the same value being plugged in, we have shifted value plus delta, right? And so the idea is that these are going to be exactly the same values, except we'll be sort of adding on this shift here. Right? And so if that's the case for some value of delta, then under this situation, we're going to be able to use the Mann-Whitney U-test in order for us to test, are these distributions the same or are they different? That will correspond to, are the locations the same or are they different? So in order for this null hypothesis to be used, we have to be making the assumption that they have exactly the same distribution, except they might be shifted from one another. Now, it's important to note that this is going to be a very strong assumption, especially for a nonparametric test. But if we think about what we're actually assuming here, we're assuming that these two populations that we don't know the means or the locations of are otherwise exactly identical, and we're just trying to tell, are their means the same as well? This is a very strong assumption, and it's almost never going to hold in practice. And so the general advice is going to be to stay away from the use of Mann-Whitney in this context, and instead think about Mann-Whitney as testing, are the distributions the same or are they not? If the distributions are different from each other, it's likely going to be that their locations are different, but that's not necessarily going to be guaranteed. Okay? And so in order for us to think about this as a test of just the location, we have to be making this other assumption, and that other assumption is not something we're going to typically want to make. So with the idea of the test, we can also ask ourselves, well, how do we go about running it? And in order to do this, we need to end up calculating a U statistic. And the way that we're going to be doing that is to first combine and rank all of the observations. So we're going to take all of the data from X, all of the data from Y, pull that all together, and then sort that from smallest to largest. We are going to break ties using the mean rank procedure. And so the idea there is any values that are tied, you will take the mean of all of the possible ranks that they could have. Okay, and that's going to be the rank that they actually get assigned. And then what we'll do is we'll calculate our rank sum statistics for both X and Y. And the rank sum statistic, as it sounds, is going to be the sum of all of the ranks. Right? So you take the ranks of X, you take the ranks of Y, you add those up individually, that gives you a rank sum for X and a rank sum for Y. Now, given the rank sum statistics, we can use those to actually calculate what we call the U statistic. And from the U statistic, we're going to know the null distribution of the U statistic, and so we can calculate the p-value. The null distribution is going to be what we call the Wilcoxon rank sum distribution. Okay, and so the Wilcoxon rank sum distribution is going to give us our p-value here. And technically, we are going to be computing this, or formally we'll be computing this as 2 times the minimum of FU, or 1 minus F of U minus 1. Okay, and so what's going on here? Well, FU is going to be the CDF of the Wilcoxon rank sum distribution. Okay, and so we have F here and we have F here. And so the idea is that we are looking at the 2 different tail probabilities. So F of U is going to give us the probability that we observe something that is smaller than or equal to our statistic. And 1 minus F of U minus 1 is going to give us the upper tail probability. Now, the reason we're subtracting off this minus 1 here is because this is actually a discrete distribution. And so we do not end up in this case of the continuous distributions where you're able to simply go 1 minus F of U, right? So we need to subtract off this negative 1 in order for us to be taking the correct tail probability here. And then the reason that we're wanting to take the minimum of these 2 values and multiplying that by 2 is because this is not a symmetric distribution around 0, right? And so we do not actually see these 2 different values as being sort of the same as each other, and just with these U's flipping signs or whatever else might be the case. And so instead we take the smaller tail probability and we multiply that by 2. and that will give us our p-value. This is a format for p-values that actually works in essentially all of the hypothesis testing cases that are going to be common to show up, just that very often we can simplify further from here. Okay. From our p-value, we can then draw our conclusions. Okay. And so then each one of these steps we can dig a little bit more into. And so when we think about ranking the data, we are literally thinking about taking all of the data together and then sorting them from smallest to largest. Okay, so let's take a look at this example here. Suppose that we observe x is 3, 2, 9, and 8, and y is 1, 7, 3, 10, and 6. Okay? And so in order to actually rank these data, we're going to combine the sets of x and y together, and then we're going to sort them from smallest to largest. And so what does that look like? Well, when we start our combined set here, right, we take all of the data from x, so the 3, 2, 9, 8, and then we take all the data from y, 1, 7, 3, 10, and 6, and we put them all into the same set here. Okay, and then we need to start asking ourselves, well, how do we order this from smallest to largest? And that's going to be simply going through these data and looking for our smallest value. And so I think that we're going to have our 1, and then we'll have a 2, and then we'll have a 3, and there's a second 3 here. Okay, and then there's a 6, 7, 8, 9, and 10. Right, and so we just go through and we literally order them in that ranked order. Okay, so we're sorting them from smallest to largest. And when we have this written down here, I have simply said which point is coming from which data set, right? So the 1 is coming from the y data set, the 2 comes from the x data set, the 3s come from both y and x, right? So there's the one in x, there's the one in y, 6 is from y, 7 is from y, 8 is from x, 9 is from x, and 10 is from y, okay? And so in this case, we're going to have all of those points ranked here. Okay. Now, importantly, when we are looking at the ranks that are tied here, so notice that we have 3 is equal to 3 and y is equal to x here. That's going to correspond to ranks number 3 and 4, right? So if we actually were to walk through and be ranking these, we would get 1, 2, and then 3 and 4. And so the idea is that in order to assign a rank here, we're going to give each of those points a rank of 3 plus 4 over 2, which is the average of 3.5. Okay, and so then what we're saying here is that x is going to get the rank of 2 for its first point. It'll get a rank of 3.5 for its second point. It'll get a rank of 7 for its third point, and a rank of 8 for its fourth point. And so that's going to be all of the ranks for x. Y we can go through similarly. It has the smallest point. It also has one that is tied at 3.5, and then it has 5, 6, as well as 9 for the largest point here, right? So the ranks of x and y are separated out here individually after sorting the data. Okay. These ranks are all going to be then used to calculate what we call the rank sum statistics. So what is the rank sum statistics? Well, we literally take the ranks of x and y that we've just found, and we add them all up. We take the sum of the ranks. Right? So this is going to give what we call Rx and Ry, which are the sum of ranks for x and y respectively. So if we take that exact same example, then we have the ranks of 2, 3.5, 7, and 8, as well as 1, 3.5, 5, 6, and 9 for x and y respectively. And so then the rank sums are going to be the additions of all of these ranks, right? So for x, we get 2 plus 3.5 plus 7 plus 8, which gives us 20.5. And for y, we get 1 plus 3.5 plus 5 plus 6 plus 9, which gives us 24.5. Right, so we literally just add up those ranks that we found. That gives us our rank sum statistics. From our rank sum statistics, we want to calculate what we call the U statistic. And the U statistic is going to be a transformation of the rank sums. And so how do we get that? Well, first we have to calculate these intermediate values of ux and uy. And for each of them, the general format of the value is going to be to take n times m, so the sample size of x times the sample size of y, and then we're going to add on sample size times 1 plus the sample size over 2, okay, and then subtract off our rank sum. And so we do that for x, so that's here n times n, n plus 1 over 2 minus rx, and then we have the corresponding term for y. So we have the same total out front, but now here we do m times m plus 1 over 2 minus the rank at y. Once we have those intermediate values, we can define the U statistic to be the minimum of U of X, or UY, right? So U is going to be the smaller of those two. So we can actually take a look at the example that we have here, right? So we're set up on the exact same example still. We had found that the rank sum of X was 20.5. The rank sum of Y is 24.5. So therefore UX is going to be 4 times 5 times 4 plus 5, or 4 times 5 divided by 2 minus 20.5, which gives us 9.5. Or we can look at the rank sum, or the intermediate value for Y rather, which is going to be 4 times 5, same term out front, but then we take 5 times 5 plus 1 over 2 minus the rank sum of Y, which is 24.5. That gives us 10.5. Okay, and so we calculate out for both of these. Then U is going to be the smaller of those two, and we find in this case that that is 9.5. Okay. Now, these three steps are formally how we're going to calculate out our test statistic. Fortunately, there's going to be a much quicker way to do this if you're doing these calculations by hand, and so it's worth to take a look at this shortcut method, or this direct method for computation. So we can do this by simply considering the data all in sort of one step here. What we're going to do is we're going to look at either of the sets of information, either coming from X or Y, and we're going to count the number of times that each observation is higher than observations in the second set. Okay. If there are any ties, we count those observations for 0.5. Then we add up those values. That gives us what we call U prime, and U is going to be defined to be the minimum between U prime and n times m minus U prime. So let's take a look at this exact same example that we've been doing here. The general process is that we're going to go through our values for X here, and we're going to say, okay, for this 3, how many values in Y is the 3 larger than? And with 3 is larger than 1, it is the same as this 3, and so we're going to get this 1.5. And then we look at the 2, and we do the same thing, right? The 2 is going to be larger than the 1, and not larger than anything else, and so we're going to get a 1 out of there. Then we look at a 9, and the 9 is bigger than the 1, the 7, the 3, and the 6. Okay, and so that's going to give us a 4. And then we look at an 8, and the 8 is also going to be larger than the 1, the 4, the 3, or the 1, the 7, the 3, and the 6. Right, so we're going to get another 4. Okay, and so then we add up all of those values, and that's going to give us U prime, and then we calculate U from there. So going through that again, right, 3 is going to beat 1 and tie 3, right? So it beats 1 and it ties 3, and so that gives us 1.5. Okay, 2 beats 1, so that gives us a 1. 9 beats 1, 7, 3, and 6, so that gives us a 4. 8 beats 1, 7, 3, and 6, so that gives us a 4, and thus U prime has to be 1.5 plus 1 plus 4 plus 4, which is 10.5, and so then U is going to be the minimum of 10.5, and m times n, which is 20, 4 times 5 is 20, minus 10.5. And so that's going to give us 9.5 in this case, right? So we get exactly the same value, but instead of us having to do that over 3 steps, we can do that in one sort of quick and easy step. And so when you're actually calculating this by hand, I'd recommend using our shortcut method here. But if you're actually thinking about, well, why is this the rank sum test? It's because this is going to give you the exact same value as doing that rank sum statistic directly. Okay. Once we have our U statistic calculated, we can work out what is the p-value. So we know that under the null hypothesis, it's going to follow the Wilcoxon rank sum distribution, and specifically it's going to have the 2 parameters being the sample size of X and the sample size of Y. And so we can take the p-value to be the based on the Wilcoxon rank sum distribution, 2 times the minimum of the CDF at the test statistic, or 1 minus the CDF at 1 minus the test statistic. And so we can go through the process that we have here, right? So we've observed all of this. We calculated that U is equal to 9.5, and thus our p-value should be 2 times the minimum of f of 9.5 and 1 minus f 9.5 minus 1. If we actually work that out, we get a p-value of about 90% here, and so that's going to be a very large p-value in this case, right? But how could we actually get that? Well, we can use R or other similar statistical computing softwares to do this. So we take P Wilcox is going to give us the Wilcoxon rank sum distribution here. And so P Wilcox at 9.5, we take n is equal to 4, m is equal to 5. That's going to give us this first term, 1 minus P Wilcox of 9.5 minus 1, n is equal to 4, m is equal to 5. That gives us our second term. So we take the smaller of those two and then work out 2 times this, right? So 2 times the minimum of these two things gives us our p-value. And so there's a sort of misrecorded p-value up here, but that's okay, right? It's still a very, very large p-value. So the p-value should be 73% recorded up here, right? But still, this p-value is quite large. So that's going to be the way that we get the exact p-values, and that's going to work fairly well if we never have any ties and if we are dealing with a fairly small sample size. If we have a very large sample size or if we have many ties, then those p-values are not going to be reliable, and instead we have to rely on approximate p-values. And so how the approximation is going to work is through a normal approximation. And so specifically what we're going to find is that the p-value can be approximated as 2 times the normal CDF, so phi here, of the negative, and then we take our test statistic u minus m times n over 2, and then we divide by the square root of n times n plus m plus 1 divided by 12. Okay, and so this sort of weird format that we have going here, right? It's not a particularly nice form, but once we're here, this is going to give us a normal approximation to that p-value. And we should be using this whenever we have a large value for n and m, or if we have lots of ties going on, okay? Now, there is a small adjustment that improves the approximation when we have ties. We will see that adjustment a little bit later on, but for now, we will just take this approximation as it stands, okay? When you're doing the computations by hand, it's common enough to ignore those adjustments for ties, but it is important for getting a good p-value. And so if you're using software to do this, the software will always take account of the adjustment for ties. So when we had u is 9.5, n is 4, and m is 5, the approximation is going to give us a p-value of about 90.3, right? So that's going to be given to us by 2 times p-norm of the negative absolute value of u, which is 9.5 in this case, minus n times m over 2, square root n plus m plus 1 divided by 12, right? And so we calculate this out directly in R using this, and that gives us that 90.3 that we saw previously. Okay. And so once we have our p-value, we can draw conclusions, right? So we'll compare that to a level of significance, and that will be drawn relating to the null hypothesis. Note that the conclusions should be drawn related to the specific version of the null hypothesis that's being tested. And so if we're testing are the distributions equal, that's what we're actually drawing conclusions relating. If we've made the assumption that the distributions are equal except for perhaps their medians, right? If we've made that shift distribution assumption, then that would be related to the conclusion that we're drawing. So it's either going to be a hypothesis about the equality of the distribution or about the equality of the location. I'll emphasize again that equality of the distribution is probably the correct hypothesis to be testing. Okay, we can often apply this in an analogous way to the 2-sample t-test. And so in a situation that the 2-sample t-test can't be applied because of the nonparametric considerations or the parametric considerations of that test, then this will provide a nonparametric alternative. Okay. In order to do that, in order for it to be a directly analogous test, we do need that stronger assumption. And so often we'll actually be taking the distributional approach instead. So if we test equality of distributions, then we're doing this under weaker assumptions. If the assumptions are invalid, then the results may also be invalid, right? And so we have to make sure that we know what assumptions we're actually making for this test. Are we trying to test equality of locations? If so, that requires a very strong assumption, and perhaps that's fine, but we should at least be aware that that's the assumption that we're making. Okay. A couple of other points to make. The first is, what if we want to test for non-zero differences between the different locations here, right? So if we are testing fx equals fy, that's going to be the way that we actually test that, right? In the location testing paradigm, however, we're thinking about testing mu x is equal to mu y, right? Now, what if instead we wanted to test mu x is equal to mu y plus delta 0 for some delta 0 that's non-zero, right? So what if we want to test, is the difference in location equal to 10, or is the difference in location equal to -5? Okay, based on how we've set up this test, we actually can't do that yet. And so in order for us to test these types of hypotheses, if we're making those location assumptions, then what we do is we transform the data to begin. So if x has location mu y plus delta 0, then if we subtract off delta 0 from x, then x has location equal to y. And so therefore we add in this step 0, where what we're doing is we're centering the data. We take x1 minus delta 0, x2 minus delta 0, and so forth. And then that's going to allow us to test with the null hypothesis being that they are equal to one another. Okay, so then the U statistic is computed exactly as it was previously. So we can take a look at an example here now to walk through this process in general. Okay, so here we have a psychologist investigating the effectiveness of two different therapeutic approaches, cognitive behavioral therapy, so CBT, or psychodynamic therapy, PT, on reducing the stress levels in patients who have anxiety disorders. The stress levels are measured using a standardized self-report questionnaire. Higher scores indicate higher stress. So for CBT, the report scores were 25, 18, 30, 22, and 15. And for PT, the reported scores were 35, 32, 28, and 38. And we want to test whether these therapies are equivalent at alpha equals 0.05 level of significance. And so formally, what we're thinking about testing here is we want to test the null hypothesis that fx is equal to fy versus the alternative. There's a difference here. Okay, and so we want to work out, well, what is the u prime? We can then take that to get the value of u, and then we can find a p-value in this setting, right? And if we're going to be calculating u prime, what we want to do is we want to go through one of the sets of scores, and so we can take CBT, and then we want to count out, well, how many values are each of these higher than from the other set. Again, so if we take a look at this 25, we notice that the 25 is not higher than any of the values in the other set, and so we'll get a 0 here. And then we can take a look at this 18, same thing, right? So we'll get another 0. For this 30 is going to be higher than the 28 here, but nothing else. So then we get a 1. This 22, that's not higher than anything. And this 15, that's not higher than anything. And so that's 2 more zeros, right? And so u prime is actually going to be equal to 1 here. U is going to be the minimum between n times m, which in this case we have 1, 2, 3, 4, 5 individuals from the CBT group and 1, 2, 3, 4 from the PT group. And so we're going to get 5 times 4 is 20 minus 1 and 1. And so the minimum is also going to be 1, right? And then to calculate out our p-value, we're going to want to take 2 times the minimum. And then here we will take f of 1, or 1 minus f of 1 minus 1. And we could look this value up using statistical software or similar. Okay, and so that's the general idea. We can walk through that all again here to make sure that we get towards those answers, right? So we're testing, are the distributions equal versus the alternative that they are not equal, right? We calculate u directly. So we have 35 beating 5 of the points, 32 is beating 5 of the points, 28 is beating 4 of the points, and 38 is beating 5 of the points. So what we're actually doing here is we're working from this group and looking over here, okay? And it's going to work out to be exactly the same, right? And so we will find 35 beats 5, so 35 is beating everything, 32 is beating everything, 28 is beating all of the points except for the 30, and 38 is beating everything as well, right? And so we get sort of the full value there. That's going to sum up to 19. U is going to be the minimum of 4 times 5 minus 19, or 19, which is 1, which is exactly what we got calculating it in the other direction as well. So it doesn't matter which you take as your base, right? It's going to give you the same answer no matter what. And so then the null distribution is going to be a Wilcoxon rank sum distribution with 4 and 5, which will be approximately a normal distribution with 10 and 50 over 3, plugging in those values from our normal approximation. Okay. So then we can grab out our p-value in this case. So we take 2 times the minimum fu and 1 minus f of u minus 1, right? Or we can approximate that using our approximation formula. In R, we can do this based on the p-Wilcox, right? So p-Wilcox of 1, n equals 4, m equals 5, or using the p-norm sort of equivalent here. And in the case of our exact p-value, we get this estimated value of about 0.03. And then if we were using the normal approximation, we'll get a value of about 0.027. Okay. And so in this case, right, if we're testing at the alpha level of 0.05, both of the exact and the approximate values are going to be below the level of significance, and so we will be able to reject the null hypothesis. Now, in this case, because our sample sizes are small and because there are no ties, we really should be using that exact p-value here. Okay, and so the p-value is going to be less than the level of significance, and so we reject the null hypothesis. As a result, we conclude that CBT and PT do have different results or different impacts on the stress levels of patients with anxiety disorders, right? There is actually a difference in their distribution. Second example here, an economist is interested in understanding if there's a statistically significant difference in job satisfaction between employees in the marketing and finance departments of a large company. So they go out, they collect information from 10 employees, giving their satisfactions on a scale of 1 to 5. For marketers, the ratings were 5, 4, 3, and 4. And for finance, those ratings were 1, 4, 4, 3, 2, and 1. Okay, and so then we want to test the researcher's hypothesis. Is there any difference or not at an alpha of 0.1? Okay, and so here, once again, we can think about testing this null hypothesis as either fx equals fy versus the alternative of fx not being equal to fy, or alternatively, if you're willing to assume that the distributions are exactly the same except for perhaps their median, right? And maybe that's something that you would be willing to assume if you worked in this company and you understood the long-term satisfaction. We can frame this as, is the location of x equal to the location of y, or are they not, right? In either situation here, we're going to want to work out u prime. We're going to want to work out what u is, and then we can find our p-value here. And so again, working out u prime, right, we do this sort of directly. We can start here looking at the set of data, and we're asking ourselves, well, how many points is 5 larger than? And 5 is larger than everything, right? So there are 6 over here, and so that first one's going to give us a 6. We do the same thing asking for this 4 here, and the 4 is going to be larger than 1, 3, 2, and 1, so that gives us our 4, and it's the same size as the other 4 here, and so we get 0.5 for this and 0.5 for that, and so that's a total of 5, right? So we get 6 plus 5. We then look at the 3. The 3 is larger than the 1, the 2, and the 1, and it's tied as the 3, and so that's going to be 3.5. Okay, and then we've already worked out the 4 is 5 here, okay, and so that should give us 19.5. If we then look at u, that's going to be the minimum of m times n minus 19.5 or 19.5. In this case, m times m is going to be 24, right? 6 times 4 is 24. So that's 24 minus 19.5 or 19.5. And for us here, that's going to give us a 4.5. Okay, and so then our p-value here, in theory, is going to be equal to that 2 times the minimum of the Wilcoxon rank sum distribution. However, notice that we have multiple ties here, right? So we have the 4. There are a total of 4 4s in this data set, and there are a total of 2 3s in the data set. And so as a result, because of the ties, we should really be approximating this using our normal approximation here, right? And so that's going to be the general approach that we take. So we can look at all of that coming together here. So we test the null that the distributions are equal versus the alternative that they're not equal. Again, here it might be reasonable to make this a location test depending on what we know about the setting. We can compute u directly. Doing that, we get the 5 beating the 6, 4 is beating 4, ties for 2 for the total of 5, 3 beats 3 and ties for 1 for a total of 3.5. And so we get that 19.5 for u prime. U is going to be the difference of 24 minus 19.5 or 19.5, which gives us that 4.5. And the null distribution should be this Wilcoxon sign rank, which is approximately equal to the normal 12-22 distribution. Okay, so actually running through this test, we could take a look at that Wilcoxon p-value here. However, we should really be thinking more about this normal approximation, which is going to be the difference, or 2 times the phi of negative difference u minus 12 over the square root of 22. Okay, and so either using p-Wilcox or p-norm gives us out our p-value, and we can see here that in both cases they're around 11%, right? So it doesn't make a big difference whether we've approximated or not, but here the approximation is going to be the more appropriate p-value. Okay. Now, From this p-value, we would fail to reject the null hypothesis, right? Because the p-value is larger than the level of significance. And so then based on the observed data, there's insufficient evidence to claim that the distributions of job satisfaction between marketing and finance are actually different from one another. The one concern we have with this is the ties that have occurred here, right? We've already indicated that there are multiple ties, and so we should really be thinking about the normal approximation. However, when we were introducing that normal approximation, we said that there was a tie correction, a correction that should be used if you have many ties. And so there are going to be 2 points that have 1, there are 2 points with 3, and there are 4 points with 4. That's quite a few different ties in these data. And so we should really be cautious about that and take a look at our tie correction here, right? Because here, most of our data are going to be tied. So how do we adjust for the ties? Well, it's going to be an adjustment to the variance term of our normal approximation. Okay, so the specific form of our null distribution is going to change. We should be using that normal approximation, and we're going to be modifying the variance in that normal approximation. So the way that we're going to do this is we're going to introduce this new notation, tk, and that's the total number of ties for each rank k, right? So for each of our different ranks, we go through and we ask how many points are there that have this specific rank. And then we take our corrected variance to be of the following form. So this first term here is exactly the variance that we've been using up till now, right? N times n plus m plus 1 over 12. So that's all the same. But then what we can do is we can actually subtract off this term over here. And so this term deals with our sample sizes, right? N times m over 12, n plus m minus 1. But then we have this sum over all of our possible ranks here. We take the number of points that have our rank cubed minus the number of points with that rank. Okay, and so this term becomes kind of annoying for us to deal with, right? But the idea is that it's going to depend on our sample size, and it's going to depend on how many points actually have ties. Notice that if there's any ranks that only have a single point here, we would have tk as 1 and tk is 1, right? 1 cubed is 1. And so then this is just going to be 0 and it's going to disappear, right? So this is not relevant if there are no ties. It's only going to matter when there actually are ties. And so then plugging this in, we get that our corrected p-value is going to be 2 times phi of the same format, except we have our sort of more expanded variance estimate down here. Often we're just going to write that as sigma u because, of course, this is a formula that's a little bit large to be writing out in this way. Okay, so we can go back to this example here and we can start counting up, well, what are those values of tk for us? So we've already computed u is 4.5. We're testing the null fx equals fy versus the alternative that they're not equal, right? So there are 2 different ones, and so the lowest rank is going to have a value of 2. There is only 1 2, and so then our second one is only going to have a value of 1. There are 2 3s, so T3 is 2, and there are 4 4s, so T4 is 4. There's exactly 1 5, and so then T5 is equal to 1, right? So we've just gone through and we've counted up all of the different points. If we were to sum through all of these, we'd get 2 plus 1 plus 2 plus 4 plus 1, which gives us our total number of points there, right? And so we're just counting how are those points actually dispersed among the different possible values. And so now we can work out, well, what is the variance actually going to be, right? This first term is exactly the term that we were working with before, right? So we take our sample sizes from x and y, we plug them into the formula here, okay, and then we have to look at this new term over here. And what that's going to involve is thinking about any of those points that there's actually ties for. We take the number of ties cubed minus the number of ties, right? So 2 cubed minus 2, 2 cubed minus 2, and then 4 cubed minus 4. And that will count for all of our ties that we have here. And if we work through this, we find that there is a 20.4 is the estimated variance. It's slightly smaller than what the variance was before, right? And so that's going to be useful for us. As a result, we get the approximate p-value is 2 times phi. Everything else is the same, but now we're plugging in 20.4 here. And plugging this into R, we calculate out that that p-value is actually going to be 0.0968. And so in this case, our conclusion actually does in fact change, because 0.0968, now suddenly we are below our critical value, right? So here we can use the modification for ties, then we find that the p-value is less than the level of significance, and so we can reject the null hypothesis. Thus, we conclude that the distributions, or the locations in this case, of job satisfaction are actually significantly different, at alpha equals 0.1. Okay. And so here, the correction for ties is going to actually make a meaningful difference. If there are not that many ties relative to the amount of data you have, that correction is going to be fairly minimal. But whenever you're in a situation where there are quite a lot of ties, and especially quite a lot of ties relative to the number of data points, then you're going to want to make sure that you actually make that correction. Okay. If you run the test using software directly, it will be making that correction for you. So the Mann-Whitney U-test is going to provide a nonparametric test for the equality of distributions for independent distributions based on the ranks of the observations. It is somehow or somewhat analogous to the independent two-sample t-test. However, in order to apply it for those locations in the way that we apply the t-test, we have to make a fairly strong assumption about the underlying distributions, and it's an assumption that we're typically not going to want to make. And so instead, we're going to typically rely on the Mann-Whitney test as being a test for the equality of those distributions. Okay, it's still going to be very useful. It's going to allow us to say non-parametrically, is the distribution of one population similar to the distribution of another? And if it's not, then we're still going to be able to conclude that those things are actually in fact different.